All right, so our next topic is going to be 3.7, inverse functions. So let's start with the definition of an inverse. So an inverse is any one-to-one function where we have f of x equals y, has an inverse of f if I also have f inverse of y equals x. So we have an input or an original function f of x equals y, right? I have an input of x and output of y. An inverse function f inverse of y equals x. So I take the output from the original function, I put it in the inverse function, I get the original input back, right? So it must undo one another. We can also write that if I did a function composition as either f inverse of f of x equals x, or f of f inverse of x equals x, for all x in the domain of f, right? And again, think about that just for 1 second. If I had f inverse of f of x, whatever I put into this inner function is going to give me some value y. And whatever value y that is, when I put it into the inverse function f inverse, I need to get the original value x out in return. Right? I've already said it a couple of times, but that f, it's not f to the negative first power. That is function notation, and it means the inverse. So it's read f inverse of x. Okay. Also keep in mind, like I said, it is not a negative exponent. So f inverse does not mean 1 over f of x. Please, please, please do not do that. Okay. So a couple properties of inverses. Inverses effectively switch the x and y values for the input and the output values of a particular function. Okay, so if my regular function f has xy, my inverse function should have all the same pairs, but now in the yx order. Okay, graphically, inverses are a reflection over the line f of x because of that switching of the roles of x and y, as we saw before. And again, because we switch the roles of x and y, effectively the input and outputs, the domain of my function f becomes the range of my function f inverse, right? And the range of my original function f becomes the domain of my function f inverse, right? What I'm putting into f, I get something out, and whatever I got out of the function f has to be my input or my domain of f inverse, and thus what I get out of that function has to be the original value, the original input value from f, okay? So again, the domain of f is the range of f inverse, and the domain, or the range of f is the domain of f inverse. Okay. I'm verifying inverses. So 2 ways I can do this. All right. Here I have the conversion from Fahrenheit to Celsius. C equals 5/9 times f minus 32, and the conversion from Celsius to Fahrenheit, f equals 9/5 Celsius plus 32. So one of 2 things I could do to verify that these are in fact inverses. I could say, for instance, solve the equation here on the left, the Celsius equals formula, and find the actual inverse value. Or if you remember back a couple slides earlier, I said that f of f inverse of x must equal x. Well, I can do a composition, right? So here I could do the composition in either order, and I could take this quantity that f equals, and I could substitute it in and replace f in my other equation. Okay? My original input was c, and I need to get c out. Okay? So let's give that a shot. Let's see what happens here. All right, so if I do that, we're going to have, so this would be essentially c of f. Okay? It's kind of confusing. All right, so what I'm really going to do here is c of f of x, and I'm going to verify that they're inverses. So we're going to have 5/9 times, and instead of the function f, I'm going to substitute in my other function, so 9/5 c plus 32, and then minus the 32, and I want to verify that I do in fact get 32. So when I simplify here, right, inside of my parentheses here, right, there's nothing to be distributed to the bracket, so I can combine like terms. 32 and negative 32 are going to cancel one another out. So I'm going to have 5/9 times 9/5 C. The 5/9 and the 9/5 cancel one another out, and I get C, which was my original input value from that function. These are, in fact, inverses. So again, when I'm doing this, and here maybe using Celsius and Fahrenheit weren't the best for the first example, but what I'm doing is I'm substituting in and I'm making sure that that original input value is exactly what I get in return when I simplify f of f inverse, or f inverse of f. It doesn't matter which way we do it. So let's take another look at another problem. Here I have rational functions, and I want to verify that f and g are or are not inverses. Okay? If I go through the simplification process and I get anything other than x, then we don't have inverses. So here, let's do f of g of x. And again, I'm verifying, so I want to find out, does this equal x? Right? So when I do f of g of x, so here we're going to have 3 times the entire function, 4x plus 1 over x minus 3 plus 1, all divided by x, or 4x plus 1 over x minus 3 and minus 4. So what I'm going to start off with, I'm going to simplify in my numerator. I'm going to distribute. And one thing to keep in mind here, this 3 is the same thing as 3 over 1, so I'm going to distribute into that fraction. It's going to give me 12x plus 3 over x minus 3. Now, I'm going to do something else also because I need common denominators, right? So I'm going to create a common denominator here. I'm going to multiply by x minus 3 over x minus 3, which is going to give me this. Okay? Now, my denominator, there's nothing I can simplify there, so I have a 4x plus 1 over x minus 3. But again, I want a common denominator, so I'm going to multiply by x minus 3 over x minus 3 times that negative 4. And I'm going to have 4x minus 12 over x minus 3. Okay? I want to rewrite as single fractions in both numerator and denominator. I want to simplify here. So when I do that and combine like terms in my numerator, all right, we're going to get 13x, and the plus 3 and minus 3's cancel, and in my denominator we're going to have over x minus 3. In my numerator, or the numerator of my denominator, when I combine like terms, I'm going to have 4x minus 4x, which is simply going to be 0. And I'm going to have 1 minus negative 12, or 1 plus 12, or 13, over, still, x minus 3. All right. A couple ways I can reduce from here, but let's invert and multiply. So here I'm going to have 13x divided by x minus 3 times the reciprocal of my denominator, x minus 3, divided by 13. And if I do some simplification and canceling, the x minus 3's cancel, the 13's cancel, and I am in fact left simply with x. Therefore, f and g are inverses. All right. So my next question here is, do all inverses have functions? So normally we would talk about this in class, but can you come up with a function that when reflected over the line f of, or y equals x, will no longer actually be a function? Okay? So I'll give you a second or two to think here. If I draw a xy axis in here for us. All right, so I want to reflect something over the line, y equals x, such that when I do so, that I no longer have a function. The simplest example that I can probably come up with is a parabola. Because if I take my parabola here, let's call it y equals x squared plus 4. Okay? If I go to reflect that over the line y equals x, right? What I'm going to get is something that looks like this. And you'll notice that I no longer pass the vertical line test, right? And part of the reason for that is when I would try and solve here, right? If I try and solve that for x, I'm going to have x equals, right? I would have to subtract the 4 and then take a square root. So I'm going to end up with plus or minus the square root of y minus 4. Think about it. That's a square root that's shifted 4 units to the right. And I have two halves here, don't I? I have the upper half, or the plus case, and then I also have the lower half, or the minus case. So I in fact here have two different functions because of that plus or minus. Okay? So here is an example of something where I get an answer, but it's no longer a function. So how do we deal with that? So let's first talk about what the issue is. For a function to have a complete inverse, the function must be what we call one-to-one. What that means is that no two elements in the domain can have the same y value. So every input value, not only can it just have one output, but each output must be unique and cannot be repeated. The problem we run into with the quadratic is, for example, f of x equals x squared. I have the 0.24 and the 0.2 negative 4, or negative 2, 4, excuse me. Think about it, when I go to find my inverse then, my inverse would have the 0.4, 2, and also the 0.4, negative 2, and thus I have the same input with different outputs. We've got a problem here, right? So for something to end up being an inverse, or have a complete inverse, it needs to be a one-to-one function. So what we would have to do for a function like that is take f of x equals x squared, and I'm going to restrict the domain, in this case, all the x values such that x is greater than or equal to 0. Because now, if I think about that, that graph that I had before, right? Now what I've got, right? Here was my y equals x squared. Okay? Now what I'm doing is I'm restricting the domain so that all I really have, or all I'm really dealing with, are the values where we're actually greater than 0. Right? And what that's going to do for me is that when we reflect over the line y equals x, right, I'm going to end up with an equation that looks like this, that now, because I only have that right side, I only have the upper half of the function, or of the inverse, and I end up with something that still is an actual function. So what we're going to do is we're going to find the vertex, or that point maybe in a different irregular graph, where between a certain interval, or over a particular interval, I can define a function such that it is one-to-one. Like think about a sine function, for example, right? Sine function does something like this, right? When we actually go to find the inverse here, right, in a sine function, actually, excuse me, let me go back. With the sine function, we define the inverse from negative pi halves through pi halves. We define the inverse over this interval here because that's what's one-to-one. So typically we're going to find the vertex, or possibly a point between or over a certain interval or a certain range that's going to allow us to be one-to-one. So find the vertex, and we're going to restrict such that the function is now one-to-one. Okay. So again, in a lot of our polynomial functions or our family functions, we're going to find that vertex, that locator point, that center point of the graph. When you look at some of the periodic functions like sine, cosine, tangent, cotangent, so on and so forth, we're going to have to find a specific interval over which we are 1 to 1, and it's not necessarily going to be the center of the graph. We just need an interval and the most complete interval over which we are 1 to 1. All right. So a couple of steps for finding inverses. All right. First and foremost, check to see is the function 1 to 1, and if it's not, we're going to restrict the domain so that the original function then becomes, or the restricted function becomes 1 to 1. I'm going to replace the f of x with y. Right? It just simplifies the process, makes my life a little bit easier, and saves me some writing. And then what we're going to do is we're going to switch all the x and y's in the entire equation. So everywhere we had an x, it's now going to be a y. So you may have multiple y's in an equation, right? And that value or that spot where there wasn't a y is now going to be your single x. And what I want you to do then is solve for the new y. Once you've solved for the new y, you now have your inverse function. So you can rewrite the domain, right? If you have something like quadratic, when you find the inverse, you now have a square root, which has a domain that's already restricted on its own. So you're going to have to restrict that domain. Also, and I don't have it written here, but in step 4, then you're also going to write as f inverse of x once you get to that point. And the last step, right? In the first 5 here, what I'm really looking for when I'm checking something on a test or a quiz right now. Okay, I'm looking for the work, I'm looking for the domains, the ranges, and all of that. Step 6 is your check to make sure that you actually did everything correctly. Okay, it would be in your best interest to evaluate f of f inverse of x or f inverse of f of x. Doesn't matter which one, but it would be a good idea to at least check one of those to make sure that you have inverses. Or graphically, using the graphing calculator, graph both of them and also the line y equals x, and look to make sure that you do in fact have a reflection over that line y equals x. So I've got a couple examples here, right? And we're going to do one on each page. So the first one, f of x equals 4x minus 3, right? I'm also going to list my domain and my range for each function as we go. So here's a linear function. My domain and my range are both all reals. Linear functions are 1 to 1, so I don't have to restrict anything. So we're good to go there. Step 2, I'm going to rewrite f of x as y. So we're going to have y equals 4x minus 3. Step 3, I'm going to switch all my x and y values. So I'm going to have x equals 4y minus 3. Step 4, this is where the fun happens. We're going to solve for the new y value. In this case, it's not going to be too bad, but we're going to solve for the new y. So I'm going to add 3 to both sides, giving me x plus 3 equals 4y. And then I'm going to divide everything by 4. I'm going to have x plus 3 equals, divided by 4 rather, equals y. Or I could write that as 1/4 x plus 3/4, which makes more sense to us in terms of graphing. But I can tell you that this first way that I wrote it, where we had f inverse of x equals x plus 3 over 4, is actually going to be a little bit nicer for us in terms of verifying inverses. All right, so step 5, I've rewritten it as f of x. I still have a linear function. I want the domain of my inverse function. Domain of the inverse function is reals. My range of the inverse function, again, it's linear, is reals. All right. This is another way that you can check to make sure that you have done things correctly, because the domain of your original should now be the range of your inverse, and the domain of your inverse should be the range of your original function. But here, because they're all reals, it doesn't really help us a lot. Step 6, our check, right? So if I evaluate f of f inverse, all right, so I'm going to have 4 times x plus 3 over 4 and minus 3. All right, the 4's are going to cancel, leaving me x plus 3 minus 3 plus 3 minus 3 cancels, leaving me with x. These are, in fact, inverses. We're good to go. Right? Again, everything's here on the left is what I'm really looking for, along with the domain and range of the function and inverse. The check, that's for you to make sure that you did things correctly. I'm not necessarily looking for that. All right? Let's take a look at the next one. All right? F of x equals x squared plus 1. All right? So the domain of this function, right? And if I sketch what this function is going to look like, just should have done the last one, but it didn't. So this is going to be a parabola that is shifted up 1 unit. Right? I have a problem though, because this function is not one-to-one. Right? So I need to restrict my domain. I want to get rid of this left-hand side in my function. I only want to look at the right-hand side here from my vertex. The vertex here was at 0, 1, so I want to restrict it to the right. So I'm going to restrict the domain from 1, or from 0 rather, through infinity. Okay? My range here is still going to go from positive 1 through infinity. Okay? I want something that when I find my inverse is going to be reflected over the line y equals x. So step 1, I've restricted the domain appropriately. Step 2, we're going to rewrite f of x as y. Step 3, I'm going to switch all my x's and y's. So I'm going to have x equals y squared plus 1. And step 4, we're going to solve for the new x. So I'm going to subtract 1 on both sides. Then here, I'm going to then take a square root. Now, because I've restricted the domain, this is one of the few places in math where you can ignore the plus or minus. I've gotten rid of that minus case by restricting the domain to the right or the positive side from that center point. Right? So I don't need a plus or minus here. Right? Step 5 then, I can rewrite this as f of x, or f inverse of x rather, as square root of x minus 1. So the domain of my inverse, right, domain, this is going to be a square root function shifted 1 to the right, so 1 through infinity. And my range of the inverse doesn't shift up or down at all, it opens upward. It's going to go from 0 through infinity. This graph is going to look something like this. So over here I had f, here I have f inverse. And it is in fact a reflection over the line y equals x for all of these points. Okay? If you take a look, you'll see the domain of my original function is the range of my inverse. The range of my original function is the domain of my inverse, as they should have been. Verification, step 6. Let's do f of f inverse. And again, it doesn't matter which order you do the substitution in. All right, so here I would have quantity square root x minus 1 all squared plus 1. The square and the square root cancel, leaving me with x minus 1 plus 1. Minus 1 plus 1 cancel, leaving me with x. These are, in fact, inverses. We're good to go. All right? Let's take a look at another problem. So here I have a square root function. This is square root of x minus 3. This is going to be a square root function that shifts 3 units to the right, opens upward, and looks something like this. Again, when I find the inverse, I want something that's going to look like a reflection over the line y equals x. So, domain of my original function. This again is square root that shifted to the right 3. This is 3 through infinity. The range of my original function, it doesn't shift up or down at all, and it opens upward, so 0 through infinity. Right? It is a one-to-one function, so I do not need to restrict any domains further than the restriction from the function itself. All right. Step 2, rewrite as y. So y equals square root x minus 3. Step 3, replace or switch x and y. So I have x equals y minus square root of y minus 3. Step 4, I now want to solve. All right. So in solving this, first thing I'm going to do, isolate the square root if possible. Right? It's already isolated, so I'm going to square both sides. So I'm going to have x squared equals y minus 3. And my next step, I'm going to add 3 to both sides. I'm going to have x squared plus 3 equals y. Right? Step 5, I've solved for the new y, so f inverse of x is going to equal x squared plus 3. Right? So domain of my inverse, range of my inverse. Right? Domain of this, if you think about it, it's now a square root. It would be all reals is a square root, but think about this. I only have 1/2 of this function. The only half when I reflect it that I can get is the right-hand side of that original function then, okay? Based on that restriction we had before, right? My domain here is still going to only be from 0 through infinity because this is only going to give me the right-hand side of that inverse, right, for f inverse. Right, my range shifted up 3 units, it's going to go from 3 through infinity. Right, my domain and range did switch, so it tells me it should be an inverse. We can verify it real quick. Step 6, if I do f of f inverse, right here I'm going to have square root of, we're going to have the quantity x squared plus 3 minus 3, right? The plus 3 minus 3 cancel, so I have square root of x squared. Square root and square cancel, I'm left with x. They are in fact inverses, they check out. Now I want to find the inverse of the next function. This poses a problem for me, right? Right now I have f of x equals x squared plus 4x plus 1, right? So the problem that I'm going to run into here is I don't know where the vertex is. So first thing I need to do is find that vertex. So for the vertex, I'm going to find the x coordinate opposite of b over 2a. So the opposite of 4 over 2 times 1. I'm going to get negative 2. For the y coordinate, right, I'm going to plug that negative 2 in. So I'm going to have negative 2 squared plus 4 times negative 2 plus 1. We're going to have 4 minus 8 plus 1, or we're going to have a y coordinate that is negative 3. Okay, so I have a vertex here at negative 2, negative 3. All right, so if I sketch this at negative 2, negative 3, so somewhere maybe down about here, I'm going to have function drawing that might look something about like that. Okay. Right. So here I'm going to have to restrict my domain, and I already did it in my graph. Right. I'm going to restrict the domain from negative 2 through infinity. My range is going to go from negative 3 through infinity. All right. Over step 1. Step 2, I want to replace f of x with y. And step 3, I'm going to switch x and y. Okay, now I need to solve for y. All right, this doesn't factor, which doesn't really help us anyhow. Right, I have to complete the square here. Right, regardless of what the a value is, we've got to complete the square. So I'm going to isolate. So I'm going to have x minus 1 equals y squared plus 4y. Right, now I want to figure out what do I have to add to both sides here such that I have a perfect square. Right, so I'm going to figure out what do I add. So I'm going to take 1/2 of the b term. So 1/2 of 4 is 2. I'm going to square it and add it to both sides. Right, so on the left hand side here I'm going to have x plus 3 equals, and on the right hand side I'm going to have y plus 2 quantity squared. I'm going to take a square root of both sides. I'm going to have square root of x plus 3 equals y plus 2. I'm going to solve for y. I'm going to get negative 2 plus x plus 3. Okay, this was step 4. Step 5 then, I'm going to rewrite f inverse of x equals -2 plus square root of x plus 3. Right? This is a square root that's going to shift 3 units to the left and down 2. So this is going to have a domain from -3 through infinity and a range from -2 through infinity. The good news is they do both check, right? Everything works out just the way that I want it to, right? We can go back in, and if we graph this, so it's going to shift, like I said, left 3 and down 2. It's going to give me a graph somewhere right about here. I'm going to have something that looks something about like that. Okay, this graph might not be drawn perfectly to scale, all right? But it's going to give me a sketch and a good idea of whether or not I have done the right thing. Okay. Step 6, you can go ahead and verify this and make sure that algebraically this works out. Or this would be one of those cases, I'm going to tell you right now, the verification on this one's going to be kind of messy. Or the visual verification is probably the quicker, easier route. This, in fact, is correct. Our domain and range is switched. Our graphs look like it reflected over y equals x. We're good to go. Okay. Let's find the inverse of my next function. So right now, this is one that we don't really know how to graph. Okay, we haven't talked about this year, rational function. I do know that I'm going to have a domain restriction here, all right? And it will tell you that this rational function is going to be 1-to-1. Now, not all rational functions will be, but this one is. Here, my domain, and I'm going to write it as the restricted value, x cannot equal -5/3. Okay, I'm going to have a vertical asymptote, and that vertical asymptote, right, or my horizontal asymptote. Vertical asymptote is going to be the -5/3. The horizontal asymptote, right, I'm going to have a range restriction, and it's going to come from these terms out here in the front, all right, the ratio of lead coefficients in this case, that y cannot equal +5/3. And in this case, the example just happened to work out that I have a 5/3 and a -5/3. It doesn't always happen that way. Okay, so step 1, right? There is no necessary restriction. I'm going to do steps 2 and 3 together. I'm going to replace f of x with y, and I'm going to switch them to save us a little bit of work. So what we're going to have then is x equals 5y minus 10 over 3y plus 5. And I want to solve for the new y. The problem here is now I have 2 different y's. All right. The only way I can do that, I have to get that y out of my denominator, so I'm going to multiply both sides by 3y plus 5. Right? I'm going to distribute. It's going to give me 3xy plus 5x equals 5y minus 10. I want to get every term with a y in it on one side of my equation and everything else on the other side. So I'm going to subtract over that 5y. It's going to give me 3xy minus 5y equals -5x minus 10. I have a GCF here on the left, right, which is why I pulled all the terms of the y onto the left, right, because they're all y to the first, so I can factor y out as GCF. I'm going to have y times 3x minus 5 equals -5x minus 10. And my last step then, right, here in step 4, is that I'm going to divide everything by 3x minus 5. And I'm going to end up with f inverse of x equals -5x minus 10 over 3x minus 5. So if I look at my domain inverse restriction, if I set that denominator, 3x minus 5, equal to 0, and I solve it, I'm going to get that x cannot equal +5/3. And for my range restriction, again, it's going to be that ratio of lead coefficient because both of these had a degree of 1. So my y value cannot equal -5/3. And again, if I look at this, my domain and range did in fact switch, right? If I graph these, it's just going to be really confusing, but let's give it a shot. Okay, so let's do this with the graphing calculator, since this is one that you guys don't yet know how to graph. So my first equation is going to be f of x, so I'm going to have 5x minus 10 divided by 3x plus 5. My second equation, we're going to have negative 5x minus 10 divided by 3x minus 5. Oops. I want to see, let's change color for the second one. Okay. For the third one, we're going to have y equals x. And again, I want to change my color here. Let's make that blue. Okay. So if I go and graph this now, what I'm going to have, and that's what I said, I thought this was going to be really hard for you guys to see probably at this point, but there we go, it's about square. All right, if you guys do take a look here, right, I do in fact have, and my green function was the original function. If I take that function, reflect it over the line y equals x, I do in fact get the red function. Those dotted lines that you see, those are the vertical asymptotes. So for my green, our original function, we should have had a vertical asymptote or a domain restriction at negative 5/3, and I in fact do have a domain restriction at negative 5/3. For my inverse function, we said we should have had a domain restriction at positive 5/3, and I have a red dotted vertical line or vertical asymptote at positive 5/3. Now, I don't expect that you guys can graph these because, well, you haven't done them in this course, or at least at this level, really in any other courses, all right? But you should be able to at least plug it into the graphing calculator and see what it looks like. That one, just based on where everything happened to be, could be a little bit confusing if you didn't change the colors on your graphs so you can more easily see which function was which. All right, let's take a look at another example here. All right, so for this one I have 3x squared minus 5x and plus 2. So again, I know I have a quadratic. I know that my quadratic is not going to be 1-to-1, so I need to find my vertex here. So my vertex formula, the x-coordinate, is going to be the opposite of b over 2a, or we're going to have positive 5, 6. When I evaluate and find my y value here, I'm going to have 3 times 5, 6, minus 5 times 5, 6, plus 2. Let's see here, 5, 6 is going to be 25, 36. Excuse me, times 3, I'm going to have 25 twelfths, minus 25, 6, plus 2. Make myself a little bit of room here. All right, common denominator, it's going to be 12, so 25 twelfths minus 50 twelfths, and plus 24 twelfths. So if I add the positives, I'm going to have 49 twelfths minus 50 twelfths, or I'm going to have 1/12 as my y coordinate. Okay, so my domain here, right, think about my vertex, is going to be 5, 6, and 1/12. My domain is going to have to be restricted to the right of the 5, 6, so it's going to go from 5, 6 through infinity. My range, this is going to open upward, it's going to go from 1/12 through positive infinity. All right, so again, step 1, I've restricted domain. Steps 2 and 3, I'm going to switch x and y. All right, now I'm going to solve for my new x. All right, I'm going to have to complete the square again. So we're going to have x minus 2 plus some blank equals 3y plus 5y plus some blank. Now, because I'm not necessarily doing this for a graphing purpose, I can simply divide out the 3, or what I can do is I can factor the 3 out of this side of my equation. So I'm going to go back here, right, and I'm going to factor a 3 out of this side of the equation. So what we're going to get is the following then. I'm going to have 3 times y squared minus 5/3 y, plus that blank that I'm going to find here in a second. Okay? I'm now going to take that 5/3, I want 1/2 of it. It's going to be negative 5, 6. I'm going to square it. I'm going to add it to both sides. So the side's going to be 25, 36. Now, I do have one problem, one thing I didn't put in here, right? Because, oops, I didn't want all that. I just wanted this. Still, there we go. Because on the left side, this quantity that I added here is being multiplied by the 3. When I add it on this side, it must also be multiplied by a 3. Okay? Otherwise, it wouldn't be balanced. It's the one nuance here that when I factor out the 3 rather than divide it out, that it brings into play. And I'm doing it this way somewhat for a reason that we'll see here, hopefully in the end. Okay, so here we're going to have 3 times y minus 5, 6, quantity squared, equals, and if I do some simplification over here, the 3 and the 36 reduce, I have 25/12, right? And the negative 2, if I come up with a common denominator here, I'm going to have negative 24/12. So we're going to have x minus 24/12 plus 25/12, or x plus 1/12. Okay, I'm going to multiply both sides by 1/3. Right, so it's going to give me a 1/3 times x plus 1/12. And for right now, I'm not going to distribute. Equals y minus 5 over 6, quantity squared. When I take a square root of both sides, I'm going to have square root of 1/3 times x plus 1/12 equals y minus 5, 6. And when I add that 5, 6 to both sides, I'm going to get f inverse of x equals 5, 6 plus square root of 1/3 times x plus 1/12 inside the square root. This is a graph that I think it's easier to see that shifts up 5/6 of a unit. Because of the way I did this, and I have this 1/3 factored out, and I have it 1/3 times this quantity, right? It's going to shift to the left 1/12 of a unit. Okay. I'm just looking here for a second. I dropped the negative in my original part here, right? When I added all this up together, this should have been a negative 1/12, which makes this a negative 1/12 for the range. Okay. Thus, part of the reason why we actually look at the domain and ranges, because had I not done that, I might not have caught that I actually had a tiny little mathematical error up in that first part, right? Again, if I had this in its other form, it would have been 1/3 x plus 1/36. And if I would set that equal to 0 and solve it, I'm still going to get that leftward shift of 1/12, but leaving it in that factored form actually made it more apparent and easy for me. So here, again, my domain is going to be negative 1/12 through infinity, and my range is going to be 5, 6 through infinity. Again, if you really feel like being an algebraic hero, you can go back and verify this algebraically. What I would probably do, however, is I would use your graphing calculator. It's going to make your life a lot easier. So here, for the first one, we had 3x squared minus 5x and plus 2. And for my second equation, we have 5, 6 plus square root of 1/3 times x plus 1/12. And if I go and graph this, right, I do in fact see that I have inverses. Now for that first graph, it gave me the entire graph, right? On a regular TI, there is a way to restrict the domain and only show part of that graph. I feel confident that this graphing calculator app probably allows us to do that, but I'm not going to try and figure that out live on a video recording. But you should be able to do that, or at the very least, we can see here that the right-hand side of my green graph and my red graph do in fact match one another, and thus I have inverse functions. Okay, so I'll leave you guys with a thought here. All right, can you come up with a function other than y equals x that when I solve for the inverse is still a function? So I'm going to let you guys think about that a little bit, something that maybe we'll talk about in class. There are plenty of examples out here, some of which are kind of crazy, some of which are kind of cool. But let's see what you guys can come up with, and we'll go from there. All right, so have a great night, and we'll see you guys in